All right, our next topic is Chevalley-Warning theorem, and maybe I shouldn't pronounce it as warning, probably Werning, or I mean, he's a German mathematician, so there's better way of pronouncing it, but I'm not so good at such a thing. Anyway, so this is an interesting theorem in number theory of polynomials. And it was initially conjectured by Artin in 1934 and proved by Chevalley in 1935, but also and then extended by Werning in the same year. And it's true for all finite field, but we're going to state it for a simpler case when the field is Fp, so the finite field with p elements. So here's the theorem. Chevalley-Warning, 1935. So let F be a field with the size p, and p is a prime. All right, and you have many polynomials. So m be polynomials in n variables. Right. So the number of polynomials is m and the number of variables is n. If some of the degrees of these polynomials are less than n number of variables, then the number of common zeros of f1, f2, fm is divisible by p. Okay, so that's the Chevalley-Warning theorem. So when you have many polynomials, but not too many, whose sum of degree is bounded by the number of variables, then number of common zeros is divisible by p. And I will show you a simple proof discovered by Alon. And we're going to use the Federer's little theorem. If you remember what it is, this is like 1 modulo p if x is non-zero. If x is 0, then it's going to be 0, right? So let n be the number of common roots. Then you can actually write as follows. So I look at all possible assignments, and then take a product of all things like this. So what's happening here? So let's look at it in modulo p. So what's happening? On the right hand side, we have this to the power p minus 1. So when this make fi to be 0, then this is 1 minus 0. Right? So whenever this is a solution or root of this polynomial, then this will become 1. If it's not a root, this will become 1 minus 1, which is 0. So in order for this term to be non-zero, this has to be a common root. And this sum counts number of common roots, right? Modulo p. All right, so that's the simple equation. Now, let's expand the right hand side. If we expand the right hand side, we get a linear combination of monomials of the form sigma xi to the ti, right? But, oh no, not sigma, it's product. But the thing is, the degree of this polynomial is at most, so what is going to be degree? So we knew the sum of degrees is less than n, and we take a degree to the p minus 1's power, so it's going to be at most p minus 1 times n. So that's the degree. Now that means sum of the ti is at most p minus 1 times n. So the average of ti is less than p minus 1. So for some I, ti has to be less than or equal to p minus 2. Now, here's the key fact. When you add for all members of this finite field, if you add x to the t power, then it's 0 modulo p. If t is less than or equal to p minus 2. So what that means is like 0, I mean, it's like this. So maybe I can say it this way. From 0 to p minus 1. Oh yeah, let's not use, okay, n to the t. That's 0. Why? Because, well, I can ignore 0, but there is a primitive. Let g be the primitive, okay, I shouldn't say d, a primitive root, so that g squared, g cubed, g p minus 2 are distinct. One g squared, all these things are distinct. So then sum of the n to the t's power is equal to sum of g to the t's power. Right, g to the ti's power, where I is from 0 to p minus 2. And that is gt p minus 1 over g to the t minus 1. Right? But the thing is, what does that mean? So that means g to the p minus 1 times g to the t minus 1 inverse. But since we are working on modulo p, and this is not a multiple of p, so there's a multiplicative inverse in modulo p. And this term, by Feynman's little theorem, this is 0, right? So modulo p. So therefore, when you sum this, so you have this term ti, whose value is at most p minus 2. So you have something like xi to the ti power in each monomial. But sum over all xi, when you sum over this, then it becomes 0, right? So remember, we are adding x1, t1, x2, t2, x, and some constant. Well, let's ignore the constant, so xn, tn. But this is like into the same thing, but now product of j other than I, xj, tj, and then for I we're adding for all xi, we have this ti, but this term is 0, so that becomes 0. So this means the right hand side is 0. So that means n is 0 modulo p. So here's the interesting corollary. So once we have a Chevalley-Warning theorem, what do we get? So once we have this theorem, why is this theorem interesting for combinatorics? The reason is that we can say that the number of common roots is not 1. We can always say that. That is a corollary, right? Trivially, because 1 is not divisible by any, right? Right, so I'm going to show you the proof of this corollary by the Nullstrange, combinatorial Nullstrange. Because how we can prove this by using Nullstranges. And this is also due to alone. So suppose not. Suppose the number of common root is unique. So let C1, C2 be the unique common root. All right. So we define f of x1, x2, xn with a product of 1 minus fi. So now it's similar. This is similar term. Minus, now it's different. It's the product of for each j from 1 up to n, and then for each constant in f different from cj, we make a product of x minus c, xj minus c. So this is a polynomial, and now look at the but I didn't say what delta is, where we choose delta so that f of c1, c2, cn is 0. How is this possible? Well, if you look at this, if I put each xi to be a ci, then this is non-zero. So it's product of non-zero terms. So therefore I can choose delta so that this becomes something. But and also observe that delta is non-zero. Why? Because if delta is 0, then this has to be 0. But if we put c1, c2, cn, then this will become 0. So 1 minus something. So this will become 1. Right? So delta is never going to be 0. Now, this is the polynomial that we are interested. Okay. Now, this means that f of s1, x1, x2, xn is 0 for all xi in f. Right? Because if it's common root, then if there's a unique common root, for the common root you're gonna have 0. If it's not a common root, then this term will be 0 because some point this is gonna be non-zero, then 1 minus 1. Right? So by Fermat's little theorem, this will become 0, and some point some vector will be different from Cj, so this will become 0. So for any assignment, this function is 0. Right? But what is the degree? the degree of f. So when you look at this term degree is less than n times p minus 1, because sum of the degree here is less than n, so n times p minus 1. But here you're multiplying p minus 1 things and then n. So this part has degree n times p minus 1. So this is the high order term and unique coefficient. So the degree of f is n times p minus 1, and the coefficient of x to p minus 1, x and p minus 1 is going to be equal to minus delta, which is non-zero. So by the combinatorial Nurse-Renza, there is an assignment, right? There exists x1, x2, xn in f. Because f has p elements, you have this is p minus 1. So you have one. If you have one more choices, there is an assignment such that this becomes non-zero. That's contradiction, because we made sure that this polynomial is always 0. Okay? So that's a proof of a simpler statement by using the combinatorial Nurse-Renza.